12th of March was the day I was supposed to arrive, but yes, I'm here. So let's do meta quantum unique ergodicity. So as Sound was telling us, the problem is the following: we take some manifold, some space M, and then we have on this M we have the Laplace operator, and we study eigenfunctions of the Laplace operator. And if there's a boundary, then we want the function to vanish on the boundary. And we would like the function to be in L2, so we just ask phi is in L2. And after we have set up, after we asked all these things, we can ask what is the distribution of this eigenfunction. And we have seen that problem before. And here are some pictures that I took from a survey paper that Peter Sana, Christian Devote, and he has it on his website, so you can see not only the pictures but also the interesting article there. And here we take the ellipse. So M is the open ellipse. We have the usual Laplace on this ellipse. And then we ask for these eigenfunctions to be in L2. And we see here the density or the distribution viewed on the ellipse. So where it's dark, the function has bigger values. Where it's light, the function is close to 0. And you see that the distribution of the values of the eigenfunction are, in this example, in this particular space, very much not uniform. And these are not the first eigenfunctions. Somehow I forgot which value it is, but it's sort of a very high value. The 6,000th eigenfunction, and the 6,000 at first, and the second, and the third, and so on. So they are in order. They are not just picked out specifically. They are really in order. They show up like this. So for this particular system, it's unlikely that we can expect an equidistribution result, that we can expect this to go to the volume measure. This is another picture of the same phenomenon. And this one I took from a survey paper, also recent survey paper of Anantaraman and Nonnenmacher. And again, if you type in chaotic vibrations and strong scars, you find it on the internet. And here we see not the ellipse, but the circle. And again, these are a bit more hand-picked, these examples. But we see that for certain eigenfunctions, there is definitely not an equidistribution happening. And on the left, we see not an eigenfunction, we see the billiard that we have talked about before. So on the left, we see a particle that has moved to the boundary, bounced off at the boundary with angle of incidence equal angle of moving away, and so on. And then it actually produces a circle inside the bigger circle, which is something one can easily convince oneself. And the same thing actually also happens for the ellipse. There it's a bit less obvious, but even there it's true. And in some sense, that's the thing that happens, that when the dynamics the classical dynamics is easy in some sense, the technical term is when it's integrable, then we don't expect equidistribution when we look at the eigenfunctions. This stadium we have seen before is different. There, the dynamics is not integrable. If you start with some random angle and you bounce for a while, you will have no idea. You will be pretty dense in the whole space and you have no idea where you started from, and it's very, very chaotic. Except that there's this bouncing ball thing, that this up and down picture that we also have seen before. And this eigenfunction that we see here sort of remembers this bouncing periodic picture. I mean, yes. So the space is symmetric, so you definitely have something that commutes with your Laplace operator. Hence, the function could either be even or it could be odd, right? But we are looking at the absolute value squared, so we don't care about whether it's even or odd. We always see a symmetric picture. Yes. So here's the same picture again from the other survey paper. And again, we see a bouncing model up and down. And this again is the billiard played for a long time. This table, this billiard table, is different billiard table. Here, you have no parallel sides. You don't have, in the other picture, we had these two parallel sides, and we had really a whole bunch of periods, periodic orbits coming up and down. In that picture, we don't have such a thing, because when you have a periodic orbit, that's all right. You can, in the middle, jump up and down. That's a periodic orbit. But if you just a tiny bit away from this perfect vertical movement, then you will be dispersed at the north boundary. So it's sort of moving orbits that are close together, further apart. And in some sense, this picture, this dispersing billiard table, named after Sinai, is more chaotic than the stadium we've seen before. And here we see a bit of periodic orbits showing up, but much less so than in the other picture before. Anyway, so this is adding just a bit to the discussion we had before by Soundararajan, that there should be some correlation between the classical dynamics and the quantum system we discuss here. So let me tell you briefly, very quickly, what ergodicity is, because we will use this term often and frequently. So if you have a probability space and a transformation on the probability space, then we say this transformation or the measure, doesn't matter which, they are ergodic if an invariant set must be trivial. But I said we have a probability space. I didn't say that we have a topology. So somehow when I say trivial, I mean trivial in measure. And I also think that the set is trivially invariant if it's almost everything, right? So the formal thing is that if the set is invariant, then the measure of the set should be 0 or 1. So both of these things I consider as trivial, because everything is an invariant set and the empty set is an invariant set. So those are trivial examples, and if you modify these things by a null set, then it's the same thing. So an example of an ergodic system is you take the circle and you rotate by an irrational alpha. Irrational portion of a full rotation. Then you have an ergodic system. But it's not really chaotic, right? So every orbit is dense, but it's way too orderly. So it doesn't really count as a chaotic system. There's another very easy picture that explains something similar. You can take the square and, of course, glue it back together, the right-hand side to the left-hand side, the top side to the bottom side, and then what you get is the two-dimensional torus, and again you can rotate on the two-dimensional torus, but if you rotate, say, horizontally, then it's completely clear that you're not ergodic. It's completely clear that you have invariant sets that are not trivial, because a picture like this, the middle third of the square would be an invariant set of non-trivial measure. And in some sense, we see that in the billiard on the circle is a bit more complicated, but in a sense is like the horizontal rotation on the torus. So there's some, if you write down a different coordinate system, you can find an invariant like the y coordinate in the other picture. Right, and then we want to move on to the hyperbolic setting, but maybe I also state what we already heard before. Okay. So this is the theorem of Schnirelmann, Pauline, de Villers, and Zelditch that says if the classical dynamics on M is ergodic, then when we have a sequence of eigenfunctions, when we look at the full sequence of eigenfunctions that we have, and we always assume that the L2 norm is 1, so this is really a probability measure on the space, then this converges to the uniform measure, maybe not along the whole sequence, but for a subsequence of density 1. And as said before, this is the quantum ergodicity. And in the stadium picture, we saw that this might happen, right? I mean, the second picture here is uniform, but occasionally it doesn't happen, and we now know that there's actually a theorem that says that for certain stadiums it really doesn't happen along the whole sequence. It's really just the quantum ergodicity that's true and not the quantum unique ergodicity. So let me also repeat the quantum unique ergodicity conjecture. which is due to Woodnick and Sarnak. If M is a compact surface of negative curvature, then phi I squared d vol M converges to d vol M along the full sequence of eigenfunctions. So in particular, this should be true if M is the quotient of the hyperbolic plane by a lattice. And this we call the quantum unique ergodicity conjecture, which we want to discuss. So here we have a few pictures again, where we may or may not believe the theorem. A few more pictures. This is what I just wrote down. And this should also hold for H mod SL2Z. So when we take SL2Z, then we don't have a compact quotient, but we still believe that the theorem holds. So this is the theorem. And as discussed before, we look at mass cusp forms that are also Hecke eigenfunctions. We will discuss the Hecke operators a bit later, but we will do this in detail. And as was said before, the history of this is that Elon proved this for compact arithmetic surfaces. He also showed in the same paper that if gamma is SL2Z, for instance, then the limit measure may not be the uniform measure, but is a multiple of the uniform measure. That's just a quick comment. I say uniform, I say volume, I say H, and they always mean the same thing. And then Soundararajan showed last year that escape of mass cannot happen, and we hope to see something of that proof later, but not in my lecture. There's also a prehistory to this theorem. Watson showed before the work of Lindenstrauss that when you have GRH for certain L functions that show up in the problem, then you get this equidistribution result even with a rate of convergence. Right, so let me, I can leave the page, but I need to explain what this page is telling you about. We discussed that there is a relationship between the quantum problem, the study of the eigenfunctions for the Laplace, and the dynamics of the geodesic flow, or the dynamics of the billiard. There we call it the billiard. Now, what's the billiard, right? The billiard is just you take your ball and you give it a direction, and then you just let it run in that direction straight on, right? So it's sort of until you hit the boundary. But if there's no boundary, we don't have to discuss the boundary. So the analog to this for M equals H mod gamma is the geodesic flow. And there's this idea that this quantum system, quantum chaos, should have some relationship to classical dynamics, where you really have a flow. You have, what is a flow? A flow is you have a space and you have your time, and then you have a map that maps each point in the space to at a particular time to a particular time to a particular place some later time. So you have this x cross r goes to x object, and in this setting where you have h mod gamma, billiard means we want to just follow the straight line. That means we talk about the geodesic flow. And when we take the upper half plane model of the hyperbolic plane, then the geodesic orbits just look like this. So you start with a point and a vector. You always need to have a vector so that you know in which direction you are currently moving in the classical system. And this is what we are doing, but of course we are not doing this on H, we are doing this inside a quotient. So let me draw the usual fundamental domain. And then when you have here a point and a vector, you can draw the great circle. And when you flow outside of the fundamental region, then you need to use the appropriate isometry to bring you back to the fundamental region, and you keep doing that. And the gluing here is a bit more complicated, as discussed. There's some other thing happening, and so on. This is the geometric description of what the geodesic flow does. You need to work with this gluing and so on. The algebraic description is much easier because we need to understand what the unit tangent bundle of the hyperbolic plane is. And really this is just SL2R, but from the center. And when you take the quotient by SL2Z, then you have that this is the unit tangent bundle of SL2Z quotient out from H. So you have the modular surface, and then you want to attach to every point in the modular surface all the vectors in all the directions, and when you do that, you get the space SL2R modulo SL2Z. And if this is your description of the space, then the geodesic flow becomes easy, because then you just need to multiply on the right by diagonal matrices. So this is our dynamical system. We can sort of forget the geometric picture if we want. We can just say our space is this space of cosets, and our dynamics is we multiply a representative gamma g on the right by this particular diagonal matrix. That's our flow. And that corresponds geometrically precisely to following the straight vector. And we will discuss that if you have a sequence of eigenfunctions for the Laplace, if you have such a sequence, and that sequence converges to a probability measure or to a measure on the surface, then one can construct a sequence of probability measures on the, no, that's not quite true. One can construct a probability measure on the unit tangent bundle. We will show that. And after you constructed that, and you have proven that this new measure on the unit tangent bundle is invariant under the geodesic flow. This is sort of this hypothetical, currently not proven relationship between the quantum system and the classical dynamics. The idea is really when the energy goes to infinity, when the eigenvalue goes to infinity, in the limit, you should really have something that's invariant under the classical dynamical system. And what you have is a probability measure. So you have an invariant probability measure on the unit tangent bundle. And we would like to know what are the invariant probability measures on the unit tangent bundle. If we talk about the stadium or some other billiard, then we already have seen somehow a bunch of periodic points, right? And whenever you have a periodic point, you have an invariant probability measure. And these things exist in the other billiards also. You have periodic points. And whenever you have a periodic point, you have an invariant probability measure. There's also a periodic point for the modular surface. Well, there's not just one, there are many of them. But you can convince yourself it's a small game to play. If you take the great circle that hits the boundary, of course, at a normal angle, that goes through lambda and minus 1 over lambda, where lambda is the golden mean. When you draw this, and then you follow the geodesic up here, you need to use an isometry, right? The isometry moves you here, and then you actually move back here, and then you bounce off and you move back like this, and you bounce in again and you close up. It's a small game to play, and you see that the golden mean gives you a periodic orbit on the modular surface. And voila, we have an invariant measure on the space. Because whenever we have a periodic orbit, we have an invariant measure sitting on the orbit. So what invariant measures do we have? We have M is for measures. We have periodic orbits and their measures. We have the H measure. So SL2R is a nice group, it has a H measure. When you restrict the H measure to a fundamental domain of this group inside that, then you get a nice measure that goes down to X, and this is the H measure on X that's invariant not just under geodesic flow, which is what I mean here, but it's actually invariant under all of SL2R, because it's the H measure on the whole thing. And here comes the problem. For any dimension D between 1 and 3, SL2R is 3-dimensional. For any dimension between 1 and 3, there is an invariant measure whose support has dimension D. So there are really lots and lots and lots of invariant measures for the geodesic flow. It's a bit like when you take the times free map on the torus. If you take just the interval 0, 1, which is the same thing as the torus when you identify 0 and 1, and you do times 3 on that space, you have a symbolic description of the dynamics very easily by using ternary digit expansion. Right? You can expand real numbers with base 3, and then when you multiply such a number by 3 and you calculate things mod 1, you're just shifting the sequence. Now, how many invariant subsets for, or invariant measures for the shift map do you have? Some of you have many, because you can cook up rules as you go. You can say, I want to see the sequence, I want to see sequences where 0, 0, 0, 3 times in a row, never shows up. That defines you some fractal. That fractal has some dimension. If you forbid 4 zeros in a row, but not 3, your dimension goes up a bit. Of course, with this rule, you get only countable many dimensions, but you can work harder and get all the dimensions. And for the geodesic flow on X2, on this space X equals SO2 modulo SO2Z, the same thing happens. There is just too much freedom in the dynamics. Okay, so if we want to prove that quantum limits, that the limit of our sequence of eigenstates, if we want to prove that that sequence gives you in the end the uniform measure, then we need to prove more about this invariant measure than just invariance. And this is what this theorem is about, that is on the other slide. So Elon proved in his paper, where he also proved the theorem we saw before, he proved that if you take a congruence lattice over Q, so such a gamma, that is nice, then you can take the space SO2 modulo gamma, and you can look at the probability measure that is invariant under the geodesic flow. That's number one. We really want invariance. And that's something we have to show. We will have to work to show that the limit measure, we need to work to get somehow a lift of the measure from the manifold, from the surface, to a measure on the unitangent bundle of the surface. That will be work. Then we need to define the Hecke operators, and that's the second condition in Elon's theorem, that the measure should have some special recurrence properties under these Hecke operators. Again, this is something we will have to discuss and define. And then there's a third condition, namely that the entropy of every ergodic component of mu should be positive for the geodesic flow. So this is something we'll have to discuss. Entropy, and we will have to discuss what entropy of every ergodic component really means. Of every ergodic component, I can tell you, I drew you this trivial picture of the horizontal translation on a square, right? And I told you that the Lebesgue measure on the square is not ergodic for the horizontal translation because, for instance, of this set. However, if the horizontal translation is irrational, the Lebesgue measure on a single line is an ergodic measure. And you have uncountably many such ergodic measures for every height. And in some sense, well, that's Fubini, your Lebesgue measure on the square is equal to the integral of these one-dimensional measures. So there's the general ergodic decomposition theorem that says whenever you have an invariant measure, you can write it as a generalized convex combination. And you need to allow integrals in this generalized statement. You can write your invariant measures as a generalized convex combination of ergodic measures. And here's an example. And in the theorem, we don't assume that our measure mu is ergodic. However, we want to assume that every ergodic component of it, well, almost every ergodic component, should satisfy something with respect to the geodesic flow. So that's quite a good portion of his proof goes into that proof, into the proof of that theorem. And I will use this as a black box. So I will try to link the problem of quantum unique ergodicity to that theorem by showing how to construct a local lift, how to get this measure on the unit tangent bundle by discussing the Hecke operators and showing how to get this Hecke P recurrence for some prime. And then by also showing that every ergodic component has positive entropy. So this is the goal of this. And this is sort of the step one. Step one is this theorem. This theorem is the theorem of the micro-local lift. That's sort of the technology that was used by Schnirelmann, Colin de Viere, and Zeldich. However, I want to give a different construction of that micro-local lift that is in some sense not local. We will never look at charts on the manifold. Rather than that, we will always do something on all of the space at once. So it's a global construction of the micro-local lift. And yeah, Elon used this in his work, but it's not due to him. This was known before. I just don't remember who it is. So what is it saying? It's saying we take our lattice, we take the quotient of the hyperbolic plane by the lattice. Then we look at the sequence of eigenfunctions of the Laplace operator, and we want to assume that they are L2 functions, and we want to normalize them so that the 2 norm is 1. We also want them to be smooth. I mean, that's part of what we mean when we say we want eigenfunctions of the Laplace. And the eigenvalues should go to infinity. And we assume that on the phase space, we get, no, on the surface, on M, we do get the weak star limit, right? The space of probability measures is almost compact. There's this problem of escape of mass. So the space of probability or less measures, that's a compact space. So we can always ask for a converging subsequence. And then what we want to construct is, out of this eigenfunction phi I, we want to construct an eigenfunction for something else, phi I twiggle, so that when we take the appropriate density distribution, when we use these phi I twiggles again as densities, in the sense of an L2 function, then we can choose a converging subsequence again, and the limit will have two properties. It will be invariant under the geodesic flow, and when you project down again to the surface, when you ignore the angle of the vector, you should get the old measure back. Right? Maybe there's some bit of notation that I should tell you, but you could also have asked. So G is always SL2R. That might not be a surprise. K is SO2. No surprise either, but gamma, well, for this can be any lattice, but later we will always stick to SL2Z. Just because of the Hecke operators. The Hecke operators are easier to discuss in that setting. It's more classical, and I rather want to get through discussing all the various aspects rather than focusing on one aspect and then running out of time. What else? Well, M is clear. That's hyperbolic plane mod the gamma, and the unit tangent bundle of the M is then, as discussed before, SL2R mod gamma, and this is where the geodesic flow lives in. right? And we have this problem that we constructed and we are given a measure on M. On M there's no dynamics, because when I have just a point on the surface, then I don't know what to do with it. I need to know in which direction it's moving initially. I need to know a direction, then I can start moving it. So the dynamics is happening naturally on the unit tangent bundle. The Laplace eigenfunctions I have on M. So there's this step that we need to make, and this is the theorem that we need to prove. That one can take these eigenfunctions on M and do something to them so that we get functions on T1 of M. And after then taking the limit, we get a measure. So here we have mu, and then here we have mu twiggle, and this mu twiggle will project down to mu. What does that mean? That means when I integrate a function over gamma mod SL2R with respect to mu twiggle, but my function happens to be of the sort so that it doesn't depend on the k really. So it's a k invariant function. If the function is of that type, then really this function is actually a function on M. Implicitly, I'm using here something, namely that I have a nice coordinate system. Let me remind you of the coordinate system later, but finish here the sentence. So if I really have this invariant function, then this function comes from a function on M, and hence this makes sense, this equation makes sense. And this is what the projecting mu twiggle means, the L. And invariance, you probably know what that means. So, A? Yes, very good. A is the diagonal subgroup. So, I'm not quite awake, but some of you are, so good. So A is the diagonal subgroup. And I said before, when you multiply by diagonal elements, this is what the geodesic flow corresponds to. So maybe at some point there will also X appear. X is SL2R mod gamma. So X is the unit tangent bundle of M. Let me also remind you of some basic things about SL2R, which is quite important for me. There is an NAK decomposition. And N is this group, the upper unipotent group. A is the thing over here, it's the diagonal group with positive entries, and the K is SO2. And had I written here the correct thing, which I think is over square root y, and I write down 1x over square root y, 1 square root y, 1 over square root y, and cosine theta, sine theta, minus sine theta, if I get the minus at the right place, hopefully. Then the x really corresponds to the x-coordinate of a point in the hyperbolic plane, the y really corresponds to the y-coordinate of the same point of the hyperbolic plane, and the theta really corresponds to the angle of the unit vector attached to that point. Right? If I look at the hyperbolic plane, there is somewhere a point z equal x plus iy, and some angle theta that is measured starting from pointing north. So theta equals 0 corresponds to really pointing north. So my reference point, that's sort of arbitrary, but standard. My reference point is I in the hyperbolic plane, and my reference vector is the vector pointing north. That's just the ad hoc definition. And after I have chosen that particular point and that particular vector, this matrix moves that vector and that at that point to that vector and that, yeah, attached at that point. So the NAK decomposition really corresponds to my free coordinates that I like in the hyperbolic plane. Okay, so something else I want to say, namely, if you now have a smooth function on x, then whenever you have an element g in g, you can let g act on the function. How do you do this? G acted on the function f evaluated at the point x is just f at x times g. X is g mod gamma with the gamma on the left, so on the right I can still multiply, and when I do this I get an action of g on the space of functions on x. Now g is SL2R, and often when you see a Lie group, you want to also see the Lie algebra, because the Lie algebra is linear, and linear things are easier than smooth things. So if the group SL2R acts, then the Lie algebra also acts. And how does the Lie algebra act? It acts by differentiation. So you can there's an x here. You can exponentiate your m multiplied by t to get a group element, then let this group element act on the function, and then take the partial derivative of this with respect to t, and then evaluate this at t equals 0 so that the t is gone. Right? So this is the basic way in which the Lie algebra acts on the function when the group acts on the function. And when one Lie algebra element acts, you can also let another group, a Lie algebra element, act. And then you have sort of expressions like W acting on M acting on F. So you get degree 2 partial differential operators. Right? This is a fancy word of this expression is that M is a partial differential operator of degree 1 because it only takes one derivative. But this expression takes two derivatives. And there's a classical fact which I have here on the other slide, that if you take the difference of these two degree 2 differential operators where you switch the orders, then actually you get a degree 1 differential operator, which you can calculate by the two Lie algebra elements by taking the Lie bracket of the two. So this is sort of a very standard. These things are in the notes, so it's not terribly long, but it's a bit too long to discuss it in detail here. And let me just see, I think this is where I roughly want to end. The fancy phrase here is that we are talking about the universal developing algebra of the Lie algebra SL2R. but that's just the formal object you get when you allow all these formal products of elements in SL2R, but with this identification that if we have a formal product minus the same formal product in the other order, then this is the same thing as the object that is at 1 degree lower in complexity. So this can be extended to higher orders, but we actually don't need that. What we do need are degree 2 partial differential operators. Well, no surprise, the Laplace is degree 2, right? So we definitely should allow ourselves to go to degree 2. So what we will discuss next time is that there is a very important special degree 2 operator that acts on this x and is sort of a lift of the Laplace. Right, the Laplace only takes into account the x and the y coordinate. Right, the Laplace was defined as y squared partial x squared plus partial y squared. So this was the Laplace. It only looks at the x and the y coordinate. So why should we ignore the theta coordinate, or coordinate of the k? And we shouldn't. So there will be a good lift of the Laplace operator, which has nice properties. Thank you. Yes. Yes. This one? Okay. A horocycle flow is much easier. So for the horocycle flow, the classification of invariant measures is due to Fürstenberg and later Dani. So if you have a compact quotient of SL2R, the horocycle flow is what is called uniquely ergodic. There is only one invariant measure, namely the uniform measure. That's a Fürstenberg's theorem. And when you take the quotient of hyperbolic of SL2R modulo SL2Z, for instance, then you have periodic orbits for the horocycle flow. These are the horizontal orbits. And then the theorem of Dani says, these are the only other ones, the only other ergodic invariant probability measures. So then you, of course, have combinations of the two, but that's sort of understandable, right? I mean, of course, you can take the convex combination of the uniform measure and a particular periodic orbit, or a bunch of periodic orbits. You can do these things, but that's it. And this has then been generalized very successfully by Ratner and has been used in many, many ways in number theory. This case where you look at the geodesic flow, well, first of all, it's surprising that we can do anything good anyway, because as I discussed, there are these millions and more of invariant measures. And the interesting thing was precisely that Elon figured out the right conditions that he could prove, and from which he can also prove that the measure must be the uniform measure. And this is related to another conjecture of Fürstenberg, and is also related to other actions where similar theorems have been proven. But that's much more recent. I mean, that's, Elon's paper is 2006 published, but he did it several years before. So around 2000 to 2003, there were quite a few developments which I also took part in. And this is one of the highlights of the story. Yes? Yes, if you drop R, yes. So not quite true, but roughly speaking, right? Roughly speaking, entropy is dimension minus 1. So this is a cheat. But so I said there are lots of invariant measures of dimension, anything between 1 and 3. So this in particular is saying that there are lots and lots of positive entropy measures. It's not quite the same statement, but they are closely related statements. And if you have an ergodic measure, then the only ergodic component is that one measure. It's a bit harder to visualize, but maybe I manage. If you have a periodic orbit, then it's easy to see what's going on, right? If you have one of these hygienous surfaces. And a periodic orbit is easy. That's sort of just looping around one of these things. But you could also maybe say sometimes it's looping around here, but sometimes it's looping around this thing, right? There's also a loop. And it's sort of switching at random. You have an orbit that's switching at random between these two things. Sometimes it's circling a million times here, but then it's, right? And if you do such a thing, then you're roughly describing an invariant measure. If you give a stochastic way of choosing which way to go. And such a measure, if it really at random goes either to the other hole or stays on the left hole, then it has positive entropy because there are choices involved. While if it's sort of only occasionally doing it, then you can find a measure that has zero entropy but is not a periodic orbit measure. You can also do that. If it's sort of so seldomly doing the right movement and so often the other one, then you can